Thank you. And thank you to the organizers for the invitation. It's a pleasure to be here. So these are the Continuum Calogero Moser equations. Here, Q is a complex valued function, and it's a function of t and x lives in one dimension, so primes are just going to be spatial derivatives for this talk. And looking at the equation here, the linear term is just the regular Schrodinger equation, and to that we add a nonlinearity. There's a plus-minus sign. This equation has two flavors, focusing and defocusing. And every time I write a plus-minus sign in this talk, the top sign is going to be for the focusing equation, the bottom sign is for the defocusing equation. And then the nonlinearity itself is cubic. There's 3 copies of u. There's a derivative hitting 2 copies of q, and it's non-local. There's this operator C plus here, and C plus is the Cauchy-Segal projection onto non-negative frequencies. It's a Fourier multiplier that just forgets the negative frequencies of your function. This is an orthogonal projection on L2. The corresponding closed subspace is L2 plus. These are the functions in L2 with only non-negative frequencies. And a piece of classical complex analysis tells us that these are exactly the functions in L2 that can be extended to the holomorphically to the upper half plane. So we're going to be looking for solutions to this equation, not in L2, but just in the subspace L2 plus. This equation leaves L2 plus invariant. It's not a big restriction. There's also an equation on L2 minus. You just take a complex conjugate of this equation, and you can put those together to get an equation on all of L2. So if we want to study the existence of solutions, we might as well work with just the positive frequency part. And as I'll mention in a bit, this equation is relatively new to the mathematical community, but it's been floating around the physics literature for some time. The first version that was introduced was the focusing model as a continuum limit of the famous classical Calogero-Moser particle system. So here, this is a system of ODEs. We have n particles xj, which live on the line, and they're interacting pairwise through this 1 over x squared potential. And this is a repulsive potential, so pairs of particles are pushing apart on each other. And what these 3 physicists did is they took the system of ODEs and derived PDE as the continuum limit. So first we take rho here. It's a density. It consists of a delta function at each particle. And then we define V to be whatever solves this continuity equation here. And then after one further change of variables, it's this function Q which solves the focusing CCM model. And this is a physics paper. This is a purely formal computation. It's unclear as of yet how much of this can be reproduced rigorously. That's for the focusing equation. The defocusing equation actually appeared about 10 years earlier in the context of modulation theory in the setting of the Benjamin-Ono equation. So here we have the intermediate long wave equation. This is a model for if you have 2 fluids, the denser fluid below a lighter fluid, and there's an interface between these 2 fluids. They're not mixing. The intermediate long wave equation is a model for long waves at the interface between these 2 fluids. And what we're doing here is we're taking an approximately monochromatic wave packet, plugging it into this equation, and to leading order, the amplitude Q has to solve a PDE. And if you do this process for KdV, what you get is defocusing cubic NLS. So Pelanovsky did this for the intermediate long wave equation. He got a PDE which he coined the intermediate nonlinear Schrodinger equation. And in the infinite depth limit, you get the defocusing CCM equation. So just like KdV and Benjamin-Ono are linked by a family of integral equations, the intermediate long wave equations, the defocusing CCM model is linked to NLS via this family of integral equations, which Pelanovsky calls the intermediate nonlinear Schrodinger equation. Now, both of these derivations I just mentioned, CCM is coming from a completely integrable system, so it should be no surprise that the PDE we get is also completely integrable. So in particular, there's going to be an infinite sequence of conserved quantities. And the first one here is just the mass. The L2 norm is conserved for solutions to these equations. Next is the momentum here. And the first term here should look familiar from NLS, but there's this quartic correction that we have to add. And that's because the Hamiltonian structure for this equation, it's not the same as the standard Hamiltonian structure for the NLS equation, nor is it the same as the derivative NLS equation. In fact, it looks like the NLS Poisson bracket plus an extra term, and that extra term gives you this quartic correction to the momentum. And the list goes on. The next conserved quantity is the Hamiltonian. This really does induce the equation of motion through this Poisson structure. And in general, there's going to be a conserved quantity whose quadratic term looks like an HS norm squared, where S is a half integer. And then all the other terms are going to have, they're going to be higher order, they're going to have more copies of Q and fewer derivatives on each term. So if we want to study well-posedness for this system, HS spaces pose a natural candidate. And again, as I mentioned earlier, this equation is relatively new to the mathematical community. We learned about it first from this paper of Gerard and Lensman in 2022. But nevertheless, there are many known PDE techniques that can be applied here. So if you use a Kato-type iteration scheme, you can prove local well-posedness for the defocusing equation down to S equals 3/2. And then using a gauge transformation, much in the spirit of Terry Tao's gauge transformation for Benjamin Ono, you can bring local well-posedness all the way down to S equals 1/2. And when S is a positive integer, you can use those conserved quantities on the previous slide to upgrade local well-posedness to global well-posedness. On the other hand, how low can we go? And a good place to look for the answer is the scaling symmetry, which I've copied down here. This is the same scaling symmetry as DNLS. In particular, it's going to leave L2 invariant. So that identifies S equals 0 as the critical regularity. Below S equals 0, the equation's supercritical. We do not expect it to be well-posed. That leaves a gap between the known well-posedness theory and the critical regularity. And so 2 years ago, in collaboration with Rowan, Killip, and Visan, we proved that the defocusing CCM equation is globally well-posed in HS on the line all the way down to S equals 0. So here we're addressing the case of the line because the case of the circle had already been proved earlier that year by Badreddine. And here the range of S is between 0 and 1. And the restriction S less than 1 here shouldn't be taken too seriously, right? The most important space to address the well-posedness problem is S equals 0. This is the scaling critical space for this problem, and we're able to give a complete answer. We then offer a way to upgrade the regularity in order to close the gap in the known global well-posedness theory. We could keep going if we wanted to, but you'd have to work a little bit harder for each successive interval of S. We're able to treat the interval 0, 1 in a uniform manner, so we stopped there at S equals 1. This is for the defocusing equation. We can ask what's known for the focusing equation. And the picture looks very similar, with one difference. Here, we can only upgrade local well-posedness to global well-posedness for when the mass is strictly less than 2 pi. And the significance of 2 pi here is that this is the mass of the soliton. So here R is a solution to the equation, a stationary solution, decays like 1 over x. You can take this solution, you can translate it in space. You can also apply the L2 scaling, it's still a solution. You can also apply a Galilean boost and set this in motion to the right. You cannot boost it to the left, though, because that leaves the Hardy space L2+. The mass of all these solutions is the same. It's 2 pi, the mass of R here. And what we're saying is below the mass of the soliton, the conservation laws are coercive, and we can upgrade local well-posedness to global well-posedness. Now, this equation isn't just Hamiltonian, it's completely integrable. So there shouldn't just be one soliton, there should also be multi-solitons. And in general, a multi-soliton for this equation is going to look like a rational function with n poles moving around in the lower half plane. And Gerard and Lensman showed the way these poles move is exactly the Calogero-Moser system here. So earlier, the system of ODEs I had, xj was a real number. This is the same system, but now zj is a complex number. Right? So regardless of whether or not you believe the physical derivation I told you earlier, this offers another perspective in which the PDE is a continuum limit of the system of ODEs. And the mass of these solutions is quantized. In general, the mass of an n soliton is n times that of the single soliton. And what's remarkable is that once you have two solitons, they exhibit this turbulent behavior. So here I've plotted a picture of a two soliton. Remember, q is a complex valued function, so this is really the modulus of q at different time slices. And what we see in the long time dynamics is that one bump settles down and stops moving. The other bump starts moving to the right at a constant speed, but it grows vertically without bound. Now remember, the mass is conserved for this equation, so the L2 norm is the same for all of these pictures. And that's because this peak over here is growing with the L2 scaling. However, if you take a derivative of that and you look at the H1 norm, that's going to be growing in time, and that's what we're saying here at the top of the slide. Now, this really is turbulent behavior. If you look in frequency variables, right, mass is conserved, so there's the same amount of mass everywhere on the line. But in order for the H1 norm to be growing, you need frequencies moving from low to high in order for this to happen, right? So it's a cascade from low to high frequencies, and this is a key feature of turbulence. Turbulence, of course, is a topic in fluid mechanics that's been heavily studied over the past 50 years. In general, though, it's quite complicated to describe in full generality. So to have such an explicit example for an integrable system is a very exciting prospect. And this isn't just one two-soliton that's doing this. It's every two-soliton. Actually, it's every multi-soliton once you have n at least 2. So in general, if you take a 10-soliton, one soliton settles down, 9 solitons move off the page and are growing vertically. So two solitons have this turbulent behavior. On the other hand, one solitons are harmless. They either stay put or they just translate to the right. So somewhere between mass 2 pi and 4 pi, this turbulent behavior is kicking in. And initially, it was unclear where that threshold was, somewhere between 2 pi and 4 pi. And at the beginning of last year, Matt Kowalski and James Hogan proved that the mass really is 2 pi, the threshold. The moment you cross this 2 pi threshold, there are solutions that also exhibit turbulent behavior. And you have to be a little bit careful here. We don't know yet if solutions exist globally in time. So their result says either the solution is just as poorly behaved as this one is here, or it's blowing up in finite time, which would be even worse, right? And later last year, Kim and Kwan proved that actually we have blow up in finite time. They exhibited smooth solutions with mass arbitrarily close to 2 pi that are blowing up in finite time. This is the first one-dimensional integrable system I know where we have a threshold above which solutions are blowing up. Again, a very exciting prospect. By comparison, we prove that below the 2 pi threshold, the focusing CCM equation is globally well posed. Again, this is the case of the line. The case of the circle had already been resolved earlier that year. And this is for the same range of S. So on that number line I showed you earlier, this is exactly to close the gap in the known global well-posedness theory down to the critical regularity. And this result is sharp. We now know that if you increase 2 pi to 2 pi plus epsilon, you're going to have solutions that blow up in finite time. Now up next, I'm going to tell you how we prove this result. And a key step in the proof is going to be equicontinuity. So we call a family of functions f equicontinuous if the translation operator here tends to 0 uniformly over the family f. Now, if I were to replace the L2 norm here with the sup norm, this is exactly equicontinuity in the Arzela-Ascoli theorem. It still makes sense to call this equicontinuity for LP spaces because this is the condition you need to prove a precompactness theorem in LP. And this isn't any LP space, this is L2, so we have Plancherel at our disposal. And an easy exercise in Fourier variables shows that this condition is equivalent to tightness in Fourier variables. And here our functions just have support at plus infinity, so I really just care about tightness at plus infinity. And there's a good reason why equicontinuity should play a key role in our proof, because this condition here is telling you if you can prove that the orbit of your solution is equicontinuous, that condition tells you it's not concentrating anywhere in physical space. So in particular, it can't be blowing up. So as a step in proving our well-posedness theorems, we prove these equicontinuity results. So the first theorem says, given a family of functions f that's bounded and equicontinuous in L2, the corresponding set of orbits under the defocusing CCM equation is also bounded and equicontinuous. The same thing is true for the focusing equation, provided that your initial data is bounded away from 2 pi. And here, again, we now know that this 2 pi here is sharp. If you replace this by 2 pi plus epsilon, then Kim and Kwan's blow-up solutions would provide a counterexample. But also, even before that, Hogan-Kowalski's turbulent behavior solutions would already provide a counterexample for this equicontinuity result. So 2 pi really is the best we can do here. So first, before I tell you about well-posedness, I'm going to tell you how we prove those equicontinuity theorems, because we're going to need that for the proof of well-posedness. And first, we're going to need some notation. So the lax pair provides a convenient way to encode the complete integrability of this equation. We recast the PDE as this operator equation. P and L are operators that depend on Q. And we're not going to need P today, so I didn't write it down for you. But here's L. And this is an operator. You're supposed to stick a function f here on the right, and then, for example, multiply by Q bar, and then apply C plus to the product of those functions. These are operators not on L2, but just on the subspace L2 plus. And because of that, you can tell that this operator L is going to be self-adjoint. I mean, for the derivative there, that's clear. That's going to be self-adjoint. For the second part here, depending on Q, this is also going to be self-adjoint because it's of the form T star T. Likewise, P is going to be anti-self-adjoint. And that's useful because a short little formal computation shows that the solution to the lax pair at a time t is unitarily conjugate to its initial value, right? And if you take a unitary matrix and you conjugate by another, if you take a matrix and conjugate by a unitary matrix, you don't change any of the spectral information of that matrix. You don't even change the Jordan normal form, right? So this is telling you that the spectrum of your lax operator L should be conserved in time, at least formally. And we're going to use that fact to prove those equicontinuity theorems I told you about earlier. Again, what we need to prove is that given a family of initial data that's equicontinuous and bounded away from the 2 pi threshold in the focusing case, the corresponding set of orbits is also equicontinuous. And to do that, we're going to use the conservation of the spectrum of L to build a special conserved quantity. And that's this quantity here. So R is the resolvent of the lax operator. If the spectrum of L is conserved, the trace of the resolvent is also going to be conserved, the sum of the eigenvalues, right? It's going to be infinite for most Q. So here we have to subtract off the free resolvent when Q is equal to 0. But it turns out this is a finite quantity for any Q in L2, and it's automatically conserved, at least for smooth solutions. So we have a conserved quantity. What is that measuring? Now, if I take this resolvent and I expand it as a Neumann series in powers of Q, we get this down here. And the leading order term is when L is equal to 1. And we can just compute what that is. It's exactly the L2 norm of Q with this Fourier multiplier sitting inside of it. Here, kappa is a spectral parameter. It can be any positive number that's big enough, away from the spectrum of L. And what we're going to do is I'm going to take this conserved quantity I just told you about, and I'm going to take a linear combination of that and the mass. Both of those are conserved, so beta is going to be conserved as well. And I've taken this particular linear combination because the quadratic term, by what we had on the previous slide, is going to give us this multiplier here. And that is essentially a projection onto high frequencies, right? If c equals 0, that's 0. When c tends to infinity, that tends to 1. And it turns on when c is about size kappa. So this is a projection onto frequencies of size kappa and larger, essentially. And so if we want to prove that a family of functions is equicontinuous, that's equivalent to tightness in Fourier variables, which is going to be equivalent to this quadratic term tending to 0 uniformly over the family of functions f. Now that's just the quadratic term of our conserved quantity beta. However, we can prove that the full series for beta converges and is controlled by the quadratic term. So if you know the quadratic term is going to 0, the whole series is going to go to 0. Right? We get this one-way implication down here. And that's enough to prove equicontinuity. In the defocusing case, we have a good sign in the lax operator. So I have this plus sign here. And that's good because we said this second term is t star t. So it's going to be positive semi-definite. And that's helpful because when I write down, this is the trace of the resolvent minus the free resolvent. If I just subtract these two operators, combine the fractions like so, maybe put half of the free resolvent on either side to make it look symmetric, then I can drop this term here in the denominator and pick up an inequality. And what I'm left with is exactly the quadratic term of the trace. Right, so the whole trace is related to just the quadratic term. And at the level of beta, this gives me this inequality. And that's useful because the quadratic term at time t is bounded by the full series at time t, which is conserved, so it's equal to its initial value. And by equicontinuity, we know this is tending to 0. Therefore, this is also tending to 0 over here. So in the defocusing case, we have a very short proof of equicontinuity. In the focusing case, we have the opposite sign in the lax operator. Now I have a minus. And so rather than a lower bound on this term, I need an upper bound. And Girard and Lenzman proved this upper bound here, which is sharp. It's extremized by solitons. And what this says is that the best constant you can have here is the mass of Q divided by 2 pi. Right? And when the mass is strictly less than 2 pi, this constant is less than 1. And so that gives us a lower bound on the lax operator L, which in turn gives us an upper bound on the resolvent. Notice this constant here is blowing up as m gets close to the 2 pi threshold. And that doesn't finish the proof. In fact, the proof here is even longer than in the defocusing case, right? I just wanted to show you the starting point so that you could see where the 2 pi threshold appears in our analysis. Together, that's how we prove the equicontinuity results. And we're going to use that to prove well-posedness. And the way we prove well-posedness, it's not by the method of commuting flows. Rather, it's by means of an explicit formula. So here, this theorem says that if Q is an L2 solution of CCM, then it obeys this formula here. So here I have the initial data for Q, and I apply the resolvent of an operator. L is the lax operator at time 0, and then the time dependence is explicit. And X here is an extension of multiplication by X. We take the resolvent of that, apply it to the initial data. That's going to give us a function here. And then we plug that into I+. I+ just essentially integrates the function over the real line. So that's going to give you a number. That number depends on two parameters, t and z. T is time, and z, it turns out, can be anything in the upper half plane. That gives you a holomorphic function in the upper half plane, and so a function in the Hardy space, L2+, the solution you're looking for. I should mention that this explicit formula is quite special. right? Even for integrable systems, this is rare. It's now known, this is the third equation with an explicit formula. It's also known that the cubic-Sego equation and the Benjamin-Ono equation have explicit formulas, but we don't expect there to be such an explicit formula for KdV or for NLS. Nevertheless, it doesn't make the problem trivial, right? In particular, it's very hard to read off the behavior of the solution from this formula. For example, these are not the operators that you encountered in your first semester of functional analysis. I mean, multiplication by x is perfectly self-adjoint on L2, but we're not on L2, we're on L2 plus, and it's not self-adjoint on L2 plus. So you have to be very careful about which extension you're taking here. Likewise, I plus is integrating over the real line. You can't do that for an L2 function. This is an unbounded linear functional. So you have to equip it with a domain that always makes sense for anything that could be output by the resolvent here. So in order to prove well-posedness, what we need to prove is that given a sequence of initial data that's smooth and rapidly decaying, if it converges in L2 at time 0, then it converges in L2 at any later time, in fact, uniformly on bounded time intervals. Right? If we can prove that, that'll prove that the data to solution map extends continuously to L2. And we break the proof up into 3 steps. First, for fixed t and z, we prove that the explicit formulas are converging to something. Then we upgrade this pointwise convergence to weak convergence in L2. And then we upgrade weak convergence to strong convergence in L2 uniformly on bounded time intervals. I'm going to give you a sketch of what each of those steps looks like up next. So first, fixed t and z, we're going to say that the explicit formulas are converging to something as our initial data converges in L2. I mentioned earlier that although L, the lax operator, is self-adjoint, X isn't. But it turns out it's the next best thing. It's something called maximally accretive or maximally dissipative, depending on what your favorite functional analysis book is. Essentially what that means is that the spectrum is contained in a half plane in the complex plane. And again, there's different conventions for this. My convention is going to be the spectrum's in the lower half plane here. And what that gets you is that the resolvent exists whenever z is in the upper half plane. This exists as a bounded operator on L2. Now, if x weren't here, this operator here would be smoothing. Remember, L naught is one derivative, so this would be smoothing in HS sense by 1 degree. If I put x back in, it's no longer going to be smoothing in an HS sense, but it is still smoothing in an LP sense. In fact, we prove that this resolvent maps L2 to L infinity and L1 to L2. And that allows us to construct the full resolvent via Neumann series. So here I take this resolvent, I expand in powers of q. The linear term is the free resolvent. We said that's already bounded L2 to L2. For the next term in the series, A naught maps L2 to L infinity. We then multiply by 2 functions in L2, that brings you to L1, and then A naught smooths the output back to L2. And we could do this for every single term in the series in a way that's summable. So this tells you this operator is converging to something for any q in L2. T and z here are fixed. That's not quite what we need. What we need to prove is that if you take this q here and replace it by a convergent sequence, then these operators are converging, right? But the same estimates that work here also work for a sequence of q's. So using similar methods, we're able to prove that the resolvent, and so the explicit formula, are converging over this sequence of initial data. That's pointwise convergence. Up next, we're going to upgrade that to weak convergence. So fix a time t. Well, by conservation of mass, we know that the L2 norm of this function is the same as it is at time 0. In particular, this is a bounded sequence in L2. So by Banach-Alaoglu, we can pass to a subsequence along which it's converging weakly to something, call it q tilde. On the other hand, evaluation at a point z in the upper half plane is a bounded linear functional in L2, right? This is the Poisson kernel here, And so by weak convergence, this right-hand side is converging to Q tilde. On the other hand, by step 1, we have the explicit formula for the left-hand side. We know that's converging to something. And so we conclude that Q tilde has to agree with the explicit formula at every single point in the upper half plane. So they're the same function in L2 plus. That was just along a subsequence, but that's okay because we can start with any subsequence in the beginning, pass to a further subsequence along which this is converging to a unique limit. And so this tells you that the whole sequence is converging weakly to this limit. And then finally, in the last step, we upgrade weak convergence to strong convergence in L2 uniformly on bounded time intervals. And in order to do this, we check the hypotheses of the Arzela-Ascoli theorem. We need equicontinuity in space, equicontinuity in time, and tightness in space. There's no tightness in time. This is a bounded time interval. Equicontinuity in space, we already did that. That was theorem 3 and 4 that I told you about earlier. We just have to check the other two. For equicontinuity in time, we need this time translation to converge to 0 in L2 as h tends to 0. And I'm going to split this up into low and high frequencies. Now the high frequency part, we can make that arbitrarily small by picking n big. Now once n is fixed, I'm going to take the low frequency part and I'm going to estimate it using the fundamental theorem of calculus. That gives me a time derivative here, and then I can plug in the PDE. Normally this would be a bad move, right? I mean, the linear term is q prime prime, loses two derivatives. That's okay here because we're only looking at the low frequencies, so I can estimate that in L2 and lose a big factor here depending on n, but n is fixed. Then sending h to 0, this first term is going to go to 0 as well. That's how we prove equicontinuity in time. Finally, we need tightness in space. And this part's a little bit harder. We break it up into a few steps. The first step is not on the real axis, but if you move up by a number b into the upper half plane, we prove that the functions are tight in the upper half plane. And this is not trivial, this takes some work, right? But in a nutshell, we're using the explicit formula again here. Once you move into the upper half plane, we have a formula for the solution. Now, that's not good enough. We need to push this down to the real axis. And again, in order to do that, we're going to break it up into low and high frequencies. We can pick n so that this last term is arbitrarily small. We just have to do this for the low frequencies. And for the low frequencies, we're going to use the Poisson integral formula to go back and forth. Right? Evaluation at a point z in the upper half plane. It might look silly at first, but one way to write this is as a Fourier multiplier. Here b is the imaginary part of the number z. That's backwards though, right? We know these guys are tight. We're trying to say this guy over here is tight. So I would like to invert this operator and put it onto the left-hand side. Again, normally that's a very bad move, be terribly unbounded. For low frequencies though, I can estimate that and lose a big constant depending on n. We then know that in the upper half plane these functions are tight, so this term tends to 0 as r goes to infinity. Altogether, that finishes the proof of the Arzela-Ascoli theorem here, and so that finishes the proof of well-posedness. Now, in the remaining portion of the talk, I would like to turn our attention to some new forthcoming work. So here, at the top of the slide, I have the standard dispersive estimate for the free Schrodinger propagator, which says that if your initial data is in L1, then the solution to the Schrodinger equation is in L infinity and is decaying like 1 over square root of t. And we're going to prove a similar decay estimate in a forthcoming work for solutions to CCM, both the focusing and defocusing equation. Right? This theorem says that if your initial data is small in L2 and finite in L1, then the solution to focusing and defocusing CCM is going to decay at the same rate, 1 over square root of t, as t goes to infinity. Now, perhaps the most famous dispersive decay estimate is that for NLS. Right? For cubic NLS in one dimension, it's well known that localized and small solutions exhibit this dispersive decay with the same rate. There are many different ways to prove this, using integrability methods, using PDE methods, and different methods give you different hypotheses on the initial data. And here I've written down a few of the results. One natural choice of space here is H11, right? These are functions Q and H1, so that X times Q is also an L2. And you can get away with a little bit less regularity here. For example, here, the first index is the number of derivatives. So these are functions in L2, but we need a little bit of a weight in X to still be an L2, right? In particular, these are still localized functions. The theorem I had for you on the previous slide only had L1 and L2 hypotheses, right? That's a translation invariant space. I do not know of a translation invariant result for one-dimensional cubic NLS. Now, it might be tempting to think that somehow the explicit formula is making all of this trivial, and I assure you that's not the case. Benjamin Ono also has an explicit formula, and yet it's known that dispersive decay is false. Now, the critical regularity for Benjamin Ono is h minus a half, which is the same as L1. So you can also add a hypothesis that your initial data is small in L1, and yet we still know that dispersive decay has to fail. Right? Essentially, you take the soliton, you multiply by epsilon, and this still produces a soliton in the long time behavior, and so dispersive decay has to be false eventually. So here, this is something true, something special about CCM that's true, that we're able to unlock with the explicit formula. And again, the way we prove this is with this formula, which I've copied down here at the top of the slide. And the formula has this resolvent. And first, I'm going to just take the free resolvent when Q is equal to 0. And a short little computation in Fourier variables here shows that the combined effect of these operators is the same thing as first flowing by Schrödinger, then multiplying by x, and then flowing back by Schrödinger. The same thing is true for the free resolvent, A naught. So the full resolvent is first flow by Schrödinger, then essentially divide by x minus c, and then flow back by Schrödinger. And that's useful because in the explicit formula, I'm going to compose this with I plus. And that's what I have here at the top of the slide. So here I have the same formula we just wrote down for A naught, but now I've put I plus on the left. Remember, I plus just integrates the function over the real line. It's like evaluation at frequency 0. Well, free Schrödinger propagator, that's equal to the identity at frequency 0. So I can drop it without changing the value. And now I have an integral of something divided by x minus z. And Cauchy integral formula tells us that's evaluation at a point z in the upper half plane. That's this formula here. All of this is at the level of the free resolvent. The full formula has this resolvent here. And so again, I'm going to expand it as a series in powers of q. Every single term is going to have an A naught all the way to the left. And so I can use that formula we just proved at the top of the slide for this composition here. That's going to give me the free Schrödinger propagator and evaluation at the point z. Now, in order to prove dispersive decay, I already know the free Schrödinger propagator has a dispersive estimate. I just need to show that the input is in L1. That's what we're doing here on this slide. The linear term is easy. We're assuming the initial data is in L1, so the linear term is going to exhibit the dispersive decay that we need. The next term is also going to be okay. It's not so obvious. The reason it's okay is because we mentioned earlier, A naught is smoothing in an LP sense. In fact, it's even smoothing L1 to L infinity. And that's useful because we're going to start with initial data in L1. A naught takes that to L infinity. I then multiply by two functions in L2. That brings me back to L1. And so then we can use the standard dispersive estimate for the free Schrödinger flow. And the constants work out here. This will give you the 1 over square root of t that we need. Here, we're going to lose a factor of t, which is bad, but the operator norm of a naught exactly cancels this out. So this is very similar to the series that I showed you earlier, right? The difference here is that I only have one a naught. There's no a naught over here. And so I need to make sure that this factor of t is entirely consumed by this a naught here. And in order to do that, we need to know the initial data here is an L1. That doesn't quite finish things, right? So far, we've showed everything in square brackets here is in L infinity. But in the formula here, I'm evaluating at a point z in the upper half plane. Well, Poisson tells us how to go back and forth. That's what I have written down here. I'm going to estimate this in L infinity. This kernel here is normalized in L1. So if I smack L infinity norm on both sides, I'm going to get an estimate that's uniform in the imaginary part of z. And so what we just showed is that on any line in the upper half plane, parallel to the real axis, the L infinity norm exhibits the 1 over square root of t dispersive decay. Moreover, this estimate is uniform in B. A function in the Hardy space L2 plus, its boundary values on the real line is the pointwise limit of its values in the upper half plane. So we can just send B to 0 in order to conclude the dispersive decay estimate. And with that, I'd like to thank you for your attention.
Thank you very much for this very nice talk. Are there questions? We have time for this.
So I wanted to ask, does every term in the expansion, you showed the first two, but do they all have that same
Yes.
structure so you can
Exactly.
use the same
We're able to
integration
treat every term in the series in a uniform manner. Yes.
Thanks.
Just giving you the first term to give you the flavor.
And I actually had one other quick question. So at the beginning, this is not the main point of your talk, but you were talking about the intermediate, I forgot what it was called, but the
Intermediate NLS.
intermediate NLS equation. Yes. Is it true that in the defocusing case that if you go to the 0 depth case, you get defocusing NLS in the same way that intermediate long wave goes to KDD?
Supposedly. I haven't checked this, but okay. In theory, yes, I believe so.
Sorry? Very good. Okay, thank you.
Sorry, thank you very much for the talk. Very nice. In the limit, it's a continuum limit of infinite numbers of particles of the Calogero of Moser. But so this definition of rho, you are not rescaling by n when you That's
right. What they prove, where'd it go? What they prove is that for any finite number n, you get CCM, no error term. You get exactly focusing CCM. And so therefore, in some limit where rho is becoming a continuous function, it should be also solved as PDE.
Yeah. Mm-hmm. So you interpret it as a density even if you don't rescale by the number of particles. So what would come this sum? Is an integral? What would...
Right. It's purely formal. They're saying in some sense, if this sum of delta functions can be approximated by a smooth function rho, then it should solve this PDE. I mean, I don't know how to make sense of that for delta functions. So how to make this rigorous is unknown to me.
Okay, so...
Question?
Quick question about the dispersive decay result. Are you able to recover like a linear dependence on the initial data in L1?
What does linear dependence mean here?
Meaning like for the free Schrodinger propagator,
Oh, you want to see L1 norm of Q on the right hand side?
Yeah, I was curious if you could do that.
Yes, we can do that. So where'd it go? Whoops. Yes, you can even put the L1 norm of Q here. Make it look just like the standard dispersive estimate, still true.
So maybe another question in this area. Yes.
Like in the defocusing case, any hope of removing the delta in the
I believe that that's true, but at the moment we need a smallness assumption for both
Right.
cases.
Okay. Other questions? Yes, I have another question. In fact, I have several, but let's say just one about this new result, which is very interesting. Of course, people who are familiar with three-quartz inequalities know that for the linear Schrödinger, free Schrödinger flow, this estimate implies the L6, for instance, estimate in space-time. And it turns out that I think that Ephraim and Tataru recently, for the cubic nonlinear Schrödinger equation with what they call non-localized data, which means L2 small,
Yes, yes.
but just L2, they prove that the L6 norm is global and small too. That's what I heard from the lecture by Daniel Tataru in IHS last month, so it's rather recent.
I believe that's out. I believe that's on the archive.
Yes,
Yeah.
I think it's on the archive too. So I was wondering, is it possible to prove such an L6 estimate for this CCM equation, at least for small data in L2?
That's a very good question. I think that would be very interesting. I don't know.
Okay, because that would be a first step to something that we probably expect, which is that we have, at least for small data, we have scattering. Of course,
That
it's
would be
not
very
enough, but
Yes,
at least it would be a first step.
that would be very interesting.
Okay. If there are no other questions, let's thank the speaker again.